mostly now in physics labs when we're studying this, rather than using a double split pattern that Young did, we use multiple splits. And this is called diffraction gratings. They are more commonly used. The bright maxima produced from grating are much sharper and narrower for a double slit, allowing for better measurements. The angle of diffraction depends on wavelength, which can really be seen if non-monochromatic light is used, like a laser, right? Like if you use a red laser, it's just red light, okay? Longer wavelengths and smaller frequencies get diffracted more, and shorter wavelengths get diffracted less. So, I'll show you an example. Oh, and then so if you just had white light, which is all light coming in, it would branch off and show you all of the different colors too. So here it goes in opposite order though. If you see here it goes, you know, red, you have your Roy G. Biv going down, but then here it goes the other way. See that? It goes the other way. Because look at the violet is a shorter wavelength, and so it needs to be diffracted less so that it comes out as less of an angle. But red is a longer wavelength or smaller frequency, so it comes, whoa, so it has to be a big angle coming out. Yeah.
So how do we know which colors the lighting on?
You got to memorize it from that sheet.
Oh, okay.
Yeah. Yeah. Okay, so now something fun. I think it is. So, do you have a backside of your sheet? Like that's blank? Very last page? Yeah? Okay, go to a blank page. So, here is like a fun thing that if you looked at the light, you can see all of the colors of the rainbow. But if you look at it, it says double axis diffraction grating. It's 13,000 lines per inch, okay? Now, if I take a red light and I shine through, oh, it's not as good on, can you see it? Yeah. So if I turn this off, you can see it even better. So let's do a calculation with this one. So it says that I know that it is 13,500 lines per inch, and that's telling me that there's little slits inside of this thing, this plastic. There's really tiny slits, and there is like 13,500 lines per every 1 inch. So this is telling me information about D. But I need to go 1 divided by all of that. Because D, if we look at our notes, it says D is the distance between the slits in meters. So now we need to convert this to just meters. So if I go 1 divided by that, okay, then I kind of get rid of the lines. So go 1 divided by it. So then I end up with a value in inches. But I need to get it into meters, okay? Because that's just what it told me on here. So, now I put on there, we know that there is 2.54 centimeters per every 1 inch. So if we can set up a fraction to compare and just get it in centimeters, then we can convert it to meters. So I know I have 7.407 times 10 to the negative 5 inches. over x centimeters. Are you with me so far? Yeah? Okay. So then we just cross multiply and solve for x. Get like 1.88. Yeah. Oh, I should not use, I'm going to say that's d centimeters rather than getting mixed up with my variables. 1.88 times 10 to the negative 4 meters. Okay, so I have d to work with.
You'd be centimeters.
Oh, thank you, Lisa. Yeah. Okay, so now we convert to meters. So put centimeters on the bottom, meters on the top. There's 10 to the negative 2 meters in every 1 centimeter, or just divide by 1,000. I mean 100, sorry. So I know this. What if my question is I want to find the wavelength of my laser? Okay, so say that's my question, is finding the wavelength of my laser that I used. So what other variables do we need then? Well, if we look at our formula, say we have theta is equal to d times x over n times L. I have my d. My x is the distance between each constructive interference. So I need to measure the distance between each bright spot on there. So, well, let's see here. Morgan, you come help me.
Go on, Jesus.
So, and actually I need one more assistant.
Jim.
Okay. Okay, bring a ruler with you. Okay, so at this distance, can you mark the dots on the thing? And then Kim is going to measure the distance. Just maybe like the three that are the brightest. Good. Now Kim, measure the distance from here, where I'm holding it, to the board. Yeah, because that's the distance away. 5 centimeters. Okay. So Kim measured the distance from where I was holding the slit to the board. That was 5 centimeters. What variable was that? L. Yes, very good. So I need to convert that into meters now. Okay. Now, if I measure the distance between the dots, I get about like 1 centimeter exactly, actually. Okay, so what's,
Where did your L come from?
that Kim, when I was holding this up, okay, and I shone the light through, and he measured the dots on the, or we measured the dots, he measured this distance from the slit to the board.
Oh.
Yeah, so that's the length from where your slits are to where the screen is. See that? Yeah? Okay, good. What did I just say? Oh, we measured that the next thing was 1 centimeter. What variable is that? Is the distance from the central fringe to another fringe. Very good. And again, convert to meters. Okay, now we should make sure that our angle didn't exceed 10 degrees though. So what we do is if our length this was length, and then the distance from one maxima to the other. So if our length was 0.05 meters, and our x is 0.01 meters, what's my angle? So inverse tan that, sucker. So theta is equal to tan inverse of 0.01 divided by 0.05. No!
That sucks.
It does. So since it's 11 degrees, we need to use our other formula, which is just fine. So we are going to use the formula lambda is equal to d times sine theta over n.
I thought we could use that one.
No, we can't use the other one if it's over 10 degrees. We can use this one for everything. So our lambda is equal to the distance, what did we say it was?
1.88 times 10 to the negative
1.8
8.
times 10 to the negative 6 times by sine of that theta I just found, divided by n. Now, we assume that we measured the distance from the central maxima just to the next dot. So we assume n was 1, okay? Because it was just the distance between two of those things, okay?
So what if it's 0? Do you have to like find a limit or something?
Shouldn't be 0.
It won't ever be 0?
I don't think so. Not with the questions you'd be given. Okay, so what did you get for your wavelength? Oh, good. That sounds way better than what I got. I must have put something in there. So you take, oh, right, times 1.8. So you get 3.53 times 10 to the negative 7, right? Meters.
Do you think it?
2.12.
I know 1.8799.
Okay, let's start from the beginning together. So second 10, 0.01 divided by 0.05. Okay, we all agree on that one?
Yeah.
Okay, so sine that times by 1.88 second e negative 6. Right?
Oh, I got
Oh, I got 3.68 now.
I still got the same
It's
answer.
your sig digs, if you don't care and everything, you'll get a different.
What else do I have here?
148.
Like that?
148. It just keeps repeating.
Oh, okay. So let's include let's try and,
Now I got 3.6.
okay, let's try it, yeah. So 10,
Yeah. No kidding.
and then sine that, times by 1.8814. Okay, so I got 3.689 now? Yeah, okay. Okay, so take out that sheet, if you don't remember, take out the sheet that had all your frequencies and wavelengths of each light on it. So if this is in meters, we can convert it into nanometers too. I think we are way off.
Why? What color are we supposed to put?
Well, what color is this?
Is it different because it's a laser?
No, it shouldn't be. It should just be all red light.
Yellowish green.
So we did not get it very close, did we?
Wouldn't it be like bluish violet?
Yes. So we have a large margin of error. Because it should be,
Because we got like 3.6. That's like.
it should be about around 680 to 700 nanometers. So we have a large margin of error. So we should try it again, but I'll make you guys try it next time. You guys will do this on Monday, okay? So we can compare, so what should it be? About like, what did I say, 7.0? 6.8 to 7.0 times 10 to the negative 7 meters. So experimental minus theory divided by theory. Let's see what our margin of error is.
How do you get nanometers?
Okay, so if you go 6, well, let's
So
take
it's
what we
just
got.
to the negative 9.
Yeah, so if you go 3.68 times 10 to the negative 7 meters, and put meters on the bottom, so that's times 10 to the negative 9. Okay, so I want to see what our theory. We got 46% error.
Which
Better
numbers?
than 68.
Which numbers are we supposed to be looking at for talking about?
For what?
The color.
Well, the color is, okay, so this is for like everything here, okay? This is like a blow up version of all visible light. So it's giving you more detail. This is like farther apart, right? This is zooming in. It's a zoom in of visible light.
So,
Well, you wrote your wavelengths down here. And so this is all wavelengths. So this is 700 nanometers. This is wavelength 2, but it's a zoom in of it. Rather than saying like this general space, you know, it's giving it more detail.
so all of these are in between. these
Yeah,
two.
exactly. In between here and here and here. Okay.